Hi, this video I'm going to tell about the transaction control. So these are the outline. First we will see about what is meant by transaction concept, uh, transaction state, concurrent execution, serializability. There are two types in serializability, conflict serializability and view serializability, then recoverability, cascading rollback and cascadeless. First I will tell about what is meant by transaction. So what is meant by transaction means it is a unit of program execution that accesses and possibly updates various data items. This is a definition for transaction. Here I have given one example. Uh, in this example, the transaction is to transfer $50 from account A to account B. Okay, so normally we are sending money from one account to another account. So when we are sending a money from one account to another account, the center account money should be directed, receiver account money should be added. This is actually the concept. So same thing was done here. These are the 6 transactions. First one, we need to read the value of A. So whatever the value of A, that should be directed by 50. That will be done here. So A equal to A minus 50. Assume that my A value is 200. So after sending 50 from my account, so my amount should be 150. So A equal A minus 50. Then writing into A. So what is my A value is 150. Then I have to add that 50 into B. So then I am going to read the value of B. Assume that my B value is 50. After adding 50, so I will get 100. So B equal B plus 50. Then my B value is 100. So initially my A value is 200, my B value is 50. So after transferring, my A value is 150 and B value is 100. So what are the issues here is two main issues to deal with. The failure of various kinds. Suppose after the third transaction, my transaction is failed means my money is deducted from my account, but it is not updated in receiver's account. So this is actually the problem. Failure of various kinds. It may be a hardware failure or system crashes due to software failure also. So second one is concurrent execution of multiple transactions. These are the two main issues we need to deal with. And this is actually example, the same example I have given here. There are in transaction there are 4 properties we need to maintain: atomicity, durability, consistency and isolation. Acid properties, and first property is atomicity. So what happens in atomicity is if the transaction fails after step 3 and before step 6. So as I told, so after the third transaction, if my transaction fails means what happens is my money will be lost. So it may lead to inconsistent database state. As I have mentioned in the previous slide, so failure may be due to hardware or software. The system actually, what is the atomicity requirement is, the system should ensure that updates of a partially executed transaction are not reflected in the database. So here, after step 3, our transaction fails. So whatever the partially executed transaction, that should not be reflected in the database. That is, whatever money that is deducted, it should not be reflected in the database. This is actually atomicity. So atomicity means either complete all or none. That is actually atomicity requirement. Atomicity. So what is our requirement is, it should ensure that updates of a partially executed transaction are not reflected in the database. Second requirement is a durability. Durability means once a user has been notified that transaction has been completed, the updates to the database by the transaction must persist even if there are software or hardware failures. Suppose if we get a message like the transaction has completed, then updates to the database by transaction must persist. Even though any hardware failure or software failure occurs, update should be done in the database by the transaction. This is actually the durability. Third one is a consistency. So consistency requirement in the above example is the sum of A plus B is unchanged by the execution of the transaction. So normally what is consistency requirement is explicitly specified integrity constraints such as primary keys and foreign keys, implicit integrity constraints. Example, sum of balances of all the accounts minus sum of loan accounts must equal value of cash in hand. So this is actually called as consistency requirement. When the transaction completes successfully, the database must be consistent. The fourth requirement is isolation. So isolation between step 3 and step 6. So this is step 3 and after step 3 and before step 6, another transaction is allowed to access the partially updated database. It will see an inconsistent database state. That is, sum of A plus B will be less than it should be. Isolation can be ensured trivially by running transactions serially, that is one after another. This is actually the requirement of isolation. These are the ACID properties. ACID means A denotes for atomicity, C denotes for consistency, I denotes for isolation, and D denotes for durability. So transaction means, as I have mentioned, it is a unit of program execution that accesses and possibly updates the various data items. To preserve the integrity of the data, the database system must ensure atomicity. So atomicity means either all operations of the transactions are properly reflected in the database or none should be reflected in the database. That is actually atomicity. Consistency means execution of the transaction in isolation preserves the consistency of the database. That is actually consistency. And isolation means multiple transactions may execute concurrently, but each transaction must be unaware of other concurrently executing transactions. We can perform the transaction concurrently, but each and every transaction must be unaware other transaction is going on or other transaction is executing. That is actually isolation. And durability, after transaction completes successfully, changes it has made to the database persist even though the system failures. In case the system fails means it should not reflect in the database updation. These are the states actually. There are 5 states in transaction. One is an active, second one is a partially committed, third one is failed, fourth one is aborted, fifth one is committed. Active means it is a initial state. The transaction stays in this state while it is executing. Second one is a partially committed. So partially committed means after the final statement has been executed, it is partially committed. Failed means after the discovery, normal execution can no longer proceed. Okay, suppose if the system crashes due to hardware failure or software failure, so after we resume the the normal execution can no longer proceed. That is actually called as failed. Then aborted. Aborted means after transaction has been rolled back, the database restored it to its state prior to the start of the transaction. So two options after it has been aborted. Either we can restart the transaction or we can kill the transaction. So fifth one is a committed. So committed means after successful completion, it is called as commit. We have discussed about 3 SQL statement related to transaction. One is a commit, second one is a rollback, fourth one is a third one is a save point. This is a diagram. So initially we are in active state. This is actually active state. Initially we are in active state. When we perform read or write operation, it will go to partially committed state. So once we complete the execution, the system will go into committed state. That is a permanent story. If we are committing the transaction, it will go into committed state. Once a transaction is committed, we can terminate the transaction. In case we are in active state, suppose if our transaction failed, it will move into failed state. Even in partially committed state also, the system may fail due to hardware or software failure. So in that case also it will go into failed state. So once the system failed, we can do the rollback. So rollback, once the rollback occurs, it will changes the state from failed into aborted. From aborted state, it will go into final terminated state. So now we will see about concurrent execution. So concurrent execution, what is meant by concurrency means multiple transactions are allowed to run concurrently in the system. Advantages, it increased processor and disk utilization, leading to better transaction throughput. Example, one transaction can be using CPU while another is reading or writing to the disk. We can perform more than one operation. Suppose we are doing only one transaction. If the transaction is doing some read or write operation on the disk, then CPU may be idle. So if you are doing concurrent transaction, one transaction can be using the CPU, another transaction may be performing reading from or writing into the disk. And the response time also reduced, that is reduced to average response time. Short transaction need not wait behind longer ones. So there are different concurrency control schemes are available that we will see in the next video. Before that, we will discuss about the schedule. What are the different schedules available? So we know what is meant by transaction. Next one is a schedule. What is meant by schedule means it is a sequence of instructions that specify chronological order in which instructions of the concurrent executions are executed. Suppose assume that in the transaction we have some 3 to 4 schedules are there. So which schedule will be executed first? Which schedule will be executed next? That is actually called as schedules. In order, in which order the schedules are executing. Schedule for a set of transactions must consist of all the instructions of those transactions. I'll give one example here. This is a schedule number 1. So here we are doing 2 transactions. In first transaction, we are transferring $50 from A to B. This is schedule. This is transaction 1. And transaction 2, transfer 10% of the balance from A to B. Okay, this is actually serial schedule. What is serial schedule means? Transaction will be executed one by one. First T1 is executed, that is transaction 1 is executing, followed by transaction 2. Transaction 1, what we are doing is we are transferring $50 from A to B. So we are reading the value of A, deducting 50 rupees from A and write the value of A. Then read B, we are adding 50 to B and write B, then commit. Second transaction, transferring 10% of the balance from A to B. 10% means A into 0.1. So that is deducted from A and that value is added to B. So we are storing in temp, actually temporary variable. So that value is added with B and we are again writing into B. This is actually schedule 1, serial schedule T1 followed by T2. The same example, we can do it in different way. This is actually second schedule, serial schedule, which T2 is followed by T1. First transaction, we are transferring the 10% of the balance from A to B. Second transaction, we are sending $50 from A to B. This is a serial schedule where T2 is followed by T1. In the previous schedule, T1 is followed by T2. And schedule 3 actually, let T1 and T2 be the transaction are defined previously. The following schedule is not a serial schedule but is equivalent to serial schedule. So it is actually first one T1. Both T1 and T2, there are 7 statements are there. Here in T1, first 3 statements are executing, followed by T2 is executing 4 statements. Again T1 is executing 4 statements. Again T2 is executing 4 statements. So, but it is equivalent to the schedule number 1. Even though they are executing in different order, but it will give the same result. This is schedule number 3. But this example, following concurrent schedule does not preserve the value of A plus B, because read A equal A minus 50. So instead of reading A actually, so reading A is done in transaction 2. But what happened is here we are reading the wrong value. So A equal A minus 50 means our value is actually, assume that my A value is 100. So after deducting 50, my A value is 50. So now here A value I'm going to read 50 instead of 100. This is a problem in this schedule. And here actually we need to maintain the serializability. Okay, serializability means whenever we are doing transaction, if we are following the schedule, it should be each transaction preserves a database consistency. Consistency means the value should be correct value. Thus, the serial execution of the set of transaction preserves the database consistency. So the schedule is serializable if it is equivalent to a serial schedule. So we have two types of schedule equivalence. One is a conflict serializability, second one is a view serializability. What is conflict serializability? If a schedule S can be transformed into schedule S dash by the series of swaps of non-conflicting instructions, we say that S and S dash are conflict equivalent. So we say that schedule S is conflict serializable if it is conflict equivalent to a serial schedule. This is an example, conflict serializability example. So here schedule 3 can be transformed into schedule 6. A serial schedule where T2 follows T1 by the series of swaps by non-conflicting instruction. So T1 read A, write A, T2 again read A, write A, T1 read B, write B, T2 again read B, write B. So we are changing the schedule actually. So read A, write A, read B, write B. So this will be executed concurrently. That is, this will be considered as transaction 1. And read A, write A, read B, write B. This is T2. So this is actually conflict serializable. So even though we are doing the swapping, it is actually serializable, conflict serializable. It is this one actually it is non-conflict serializable. So T3 we have read up Q, then T4 write up Q, then T3 again write up Q. We are unable to swap instruction in the above schedule to obtain either serial schedule T3 T4 or T4 T3. So here we cannot do conflict serializable because when we are during swapping, it won't give the database consistency. It won't give the database consistency, so we cannot do the conflict serializability here. Then next one is a simplified view of transaction. We ignore operations other than read and write instructions.